Lesson 8105, Getting Coordinated, using coordinates to describe transformations. In this lesson, we'll apply transformations to points on a grid if you know their coordinates. And since this lesson is about coordinates, I want to take a moment just to remind you of how to plot points for those of you that need a quick refresher. So if I have a point like this one over here, the coordinate 3, 2, to plot that point on a coordinate grid, I have to start where these two number lines, the x-axis and the y-axis, intersect at the origin. That first number, 3, is the x value, and it tells me how far left or right I'll need to go on the x-axis. So starting at the origin, I would move 1, 2, 3 to be right under that coordinate. The second number, this red one, 2, is our y-coordinate, and it tells us how far up and down to go on the y-axis, that number line that's going up and down. So after I move 3 to the right for the x, I would use that 2 to move up 1, 2 to plot the coordinate. Let's take a look at our notes before we get into the Desmos activity today. On page 18 in your notebook today, and our learning goal is to apply transformations to points on a grid. Apply transformations to points on a grid. And once again, I'll remind you that the x value will move you left or right from the origin, and the y value will move you up or down in your coordinate. So as we're marking things today, we're going to talk about corresponding points. Here we go. So let's take a moment to really dig into what corresponding points mean. Corresponding point is a point in an original figure, or a point from an original figure. That would be the preimage. That matches up with a point on a copy. Matches up with a point on a copy, or what we would be calling the image. To illustrate this, let me draw a couple of triangles. I'm going to try and draw them exactly the same. All right, this is going to be our original figure. We'll call it ABC. And I'm going to draw a copy of that. I'm going to call this triangle DEF. Can't call it ABC again because those points have already been taken. So a point from the original figure that matches up with a point on this copy or this transformed figure, those are corresponding points. So if I were to take this green triangle and slide it to the right, point A would match up with point D. Those are corresponding points. Point B would match up to point E. Those are corresponding points. And point C would match up with point F, corresponding points. So for example, point A corresponds to point D. Sometimes we like to make sure we understand what a non-example would be. It would be wrong to say that point A corresponds to point F. If I were to fit this triangle on top of this triangle, those would not be matching up. Okay, so let's do a non-example. Point A does not correspond to point F. So those are corresponding points. One more factor characteristic that I'll mention is I'm going to bring forward something from a previous lesson about how sometimes with a transformed figure, we don't give it a new letter, but we give it that prime mark. So I'm going to say that corresponding points are sometimes labeled with the same letter, but with a prime mark. Sometimes corresponding points are labeled with the same letter. Oops, same. With a prime mark added to indicate that it's not exactly the same point. So let me just draw a segment this time. I'll call this segment AB. And I'm just going to translate it. Slide it right over here. To show that this came from segment AB, I might call this A again, but I'm going to give it a little prime to indicate it's not the same A as before. So A prime and B prime might be labeled instead of completely new letters. All right. So this is where it gets a little tricky. We're going to be applying transformation to points on a grid. I'm going to zoom in a little bit. Let me come down here. We're going to be using this point right here over and over and over and over again. So let me grab this pen here. So we have point A, and we're going to take point A and transform it according to all of these directions. So it's going to get pretty messy over here, I'm going to admit. I'm going to zoom in a little bit more actually, but I'll try and keep it tidy. Focus a little better. So I'm just going to write those coordinates, first of all, 1, 2, 3, 4, 5 times, because we're going to look at what happens to the number of the coordinate. So for all of these, we're starting with point A being -2, 1. That's -2, 1. I'm just going to write that a few times because that's where we're going to start every time. And I want to write it down so we can pay attention to what's happening to this x value and to that y value when we transform it. And probably the friendliest transformations are reflections. So let's start with a reflection across the x-axis. There's the x-axis right there. And if I were to take transparent paper, and I'm going to grab some right here, and I were to reflect across that x-axis, Tinkerbell ruler here to do that reflection. Make a line of reflection against that ruler. Just to remind us how to do that. And if I look at where it lands, the x value is the same. I'm still moving 2 units to the left, -2. But the y value is now the same distance under the x-axis as it was above the x-axis. So instead of moving to the left 2 and up 1, I'm moving to the left 2 and down 1 for my coordinate. So let me just jot down what we did there. My transformed point is now -2, -1. So we went from 2, 1 to -2, -2, 1 to -2, -1. And what happened was the x value stayed the same, but the y value changed to its opposite. X stays the same when you reflect across the x-axis. So that's what I'm talking about. We're just going to look at what happens to these numbers when we do these reflections. Reflect across the x-axis, the x value stays the same, the y value changes to its opposite. Reflect across the y-axis. Here's the y-axis here. And I bet you can predict what's going to happen. Get my transparent paper again. But this time we're going to translate across, I'm sorry, not translate. We're going to reflect across the y-axis. I'm going to make a line of reflection with my transparent paper. And when I reflect across there, this time you can see that instead of going to the left to get to my transformed point, I'm moving to the right. So instead of going -2, I'm going +2. But the y value stays the same. I'm still increasing 1. Well, you can see that under the transparent paper. So this time, pen, pink pen, our transformed point is now +2, +1. So in this case, the x value of the coordinate is opposite what it was, -2 to +2, but the y value stayed the same. So x is opposite, y stays the same. X is the first number, y is the second number. Now, honestly, I think that reflections, like we just did, are probably the friendliest ones to see, but there's patterns like this for translations and rotations as well. Let's take a look at translations. We have our point again, -2, 1, and we're told that we're going to move it right 3 units and down 2 units. Okay, so move 1, 2, 3, and down 2. It ends up at the point 1, -1. Let's think about what really happened here. If x is the number that moves us left to right along the x-axis, then if I have something telling me that I'm moving to the right 3 units, I'm going to be adding to x. I'm adding 3 to this x value. So if I take -2 and add 3, moving 3 units to the right, then my new x value is this, +1. And similarly, if we're going down 2 units, then I'm going to change my original y value. Okay? Down means I'm going to subtract. So if I take 1 and I subtract 2, got too many arrows here, don't I? I end up with this. So as I'm translating, if the amount that I'm moving left and right is how I'm going to change this original x value, and the amount that I'm moving up or down is how I'm going to change the original y value to get my transformed point. Rotations are, every rotation has a slightly different thing. You'll see the numbers, but it looks like they went through a sausage grinder. Let's take a look at these rotations, and we're not going to worry too much about coordinate rules for these, but I think you'll see that there is a relationship. So let's start with a rotation of 180 degrees with a center of 0, 0. Once again, I'm going to use my point on transparent paper. You know that the trick to rotating is to draw a little cross through that center of rotation. And I'm going to rotate that 180 degrees. Watch the cross as you rotate so you can keep track of how many groupings of 90 you've done. All right, so it says 180 rotation. Doesn't say which direction, but for a half turn, it really doesn't matter. So here we go. Here's 90 degrees. And watch that cross. I'm going to do it again. There's 180 degrees. Okay. And it looks like my point landed at 2, -1. Right there. Let's look at what happened to these two numbers. If I move 180 degrees, the x value changes to its opposite and the y value changes to its opposite. Okay, sorry if there was a little hiccup in the recording. I got cut off there, and I went ahead and talked about this next one without you. So let me go back and pick up where we left off. We just got done rotating 180 degrees, and that's a pretty friendly change. The x changes it to its opposite and the y changes to its opposite. For a 90-degree rotation, it's not quite as obvious. So I'm going to do one last rotation. This one's really the hardest one to see a pattern with. And we're told to rotate 90 degrees. It didn't tell us clockwise or counterclockwise, so I'm just going to go clockwise. Clockwise is moving to the right here, with a center of 0, 0. So I'm going to put my pencil right there on the origin. I'm going to pay attention to this cross as I rotate it. Let's look at what happens to point A. All right, looks like that cross is about 90 degrees now. And as I'm trying to read the coordinate under my transparent paper, it looks like it's now +1, +2 for my transformed point. And I've already written that down during the hiccup in the recording, +1, +2. So there's still 1s and 2s, but they've kind of switched position from x to y, and one of them got all wonkied up with changing from negative to positive. Honestly, I'm not going to worry about a 90-degree turn and a rule that goes with that, because it really changes depending on whether we're clockwise or counterclockwise. Let's see if we can summarize all of these changes. What happens to the coordinates of a point after a rotation, a translation, or a reflection? Well, let's start with the one that we started with at the top. And I'm going to write this a little symbolically here. If we have a reflection across the x-axis, whatever our x value and y value were to begin with, the x value in the transformed point will stay the same. No matter what it was before, it's going to stay the same. And no matter what the y value was, it's going to be the opposite of that in the transformed point. And if we transform or reflect across the y-axis, whatever our original two numbers were, this time it's the y value that will stay the same, and the x value will be opposite of what it was. So x will be the opposite of what it was before, and the y value will be the same as what it was before. Those are reflections. For translations, see how we can write that. So whatever our x and y value were to begin with, I don't know how to write this. We can add or subtract the amount that we're moving left or right to x. And for y, add or subtract the amount that we're moving up or down. Okay. And finally, for a rotation, we'll just talk about the 180-degree one. For 180 degrees, it wouldn't matter if we were going clockwise or counterclockwise. The original x and y would just be opposite in the transformed point. Now, when I write negative x, that doesn't mean that my number will be negative. It just means it'll be opposite of what the original one was. If the original was 2, this will be -2. If the original was -4, this will be the opposite of that, or +4. So those are some patterns that will happen with different kinds of transformations on a coordinate grid.